Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. Today's webinar is titled Long-Term Vision to Fight Advancing Water Resource Challenges, the Todd Creek Wastewater Treatment Plant Design. Our Executive Director, Dr. Daniel Other, will serve as the moderator and will introduce our speakers today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We will do our best to address each question at the end of the presentation. Before we get started, Dan would like to say a few words. Good morning, Dan. How are you?
I'm fantastic. Thanks, Marissa. Hey, Jeff and Blake, if you don't mind popping up that first slide, that would be fantastic for me. So welcome, friends. Thanks. We have another amazing award-winning webinar project today as part of the Academy's incredible webinar series. In just a few minutes, we're going to hear more from Jeff and Blake, who work for Burns & McDonnell Engineering in Kansas City. But before we get into the details of their presentation, I'd like to say thank you to the patrons of the Academy. Founded in 1955, the vision of the Academy remains leadership and excellence in environmental engineering and science. And to identify excellence, the Academy hosts an annual Excellence in Environmental Engineering and Science competition, where a panel of esteemed judges selects award-winning projects in a number of categories. And these winning projects, like today's presentation, are then shared with our membership as a way of amplifying the voices of our professional leaders. Well, how is that all possible? Well, my friends, it's all possible because of the financial support of our patrons. And who are patrons? With their firms and utilities, the logos that we share in our presentations, they've provided financial support. They put their money where their mouth is. And through their support, we're able to bring this webinar series to you, actually free to our members. Today's webinar is free to all of the members of the Academy, to our students, to our regular members, to our board-certified individuals, everyone. So please join me in saying thank you to the Academy patrons. Thank you for supporting our 5-year strategic goal to grow, connect, and diversify the environmental profession by sharing the stories of professional leaders. And that's what we're going to do today. We have a webinar where we're going to share stories of some professional leaders. It's an award-winning project. The presentation title is A Long-Term Vision to Fight Advancing Water Resource Challenges, the Todd Creek Wastewater Treatment Plant Design. And our speakers include Jeff Keller, who's the Technical Services Manager, and Blake Anderson, who's the Facilities Engineering Division Director. And these two professional engineers work at Burns & McDonnell Engineering in Kansas City, Missouri. It's a pleasure to have Jeff and Blake with us today, and thanks for joining. And colleagues, as a reminder, please put your questions in the Q&A function. I'll use these as part of the moderated discussion at the end of today's presentation. And now, Jeff and Blake, the stage is yours, my friends. We're really excited to hear from you.
All right, thanks, Dan. Can you see the screen that we're sharing?
Got it. Thank you. Hear you, no problem. Thank you so much.
Okay, real quick, I'll turn my camera on. Thanks, everybody. I'm Jeff Keller with Burns & McDonnell. Just want to do just a quick correction there. I am with Burns & McDonnell. My co-presenter today, Blake Anderson, is with KC Water, the water utility for the city of Kansas City, Missouri. We'll do some short introductions on ourselves and then jump into the project. So Blake, I'll hand it over to you to start out.
Thank you, Jeff. So basic format for the presentation is, as Jeff mentioned, introductions, a little bit of history and drivers on this project. In general, public utilities don't do 9-figure projects for no reason. Usually there's a darn good reason for them. Jeff's going to discuss some of the technology evaluation selection, a deep dive on the selected technology, which is basically an emerging technology in North America. We'll go through the facility design, the schedule, and a little bit of wrap up and questions at the end. So big picture for KC Water. So we're a department of the city. One of the pain points of Kansas City is we're 320 square miles. We have only about 500,000 people. So the low population density makes utility costs pretty brutal. We have a small rate base, and yeah, covering that much area with water and sewer service is tough. We have 2,800 miles of both water and wastewater collection systems. We have 1 water treatment plant. We have 6 wastewater plants and associated pump stations for both utilities. We're kind of what's referred to as a one water utility. We take the water out of the river, we clean it up, we move it to people, move it to your houses. You do whatever you do with it. It goes down the drain. We convey it to our treatment plants, clean it up, discharge it safely in the environment. And for extra fun, we handle all the stormwater when it rains too much. Big picture on us. We're with inflation, everything. We're around over $400 million a year in revenue utility. We serve about 600,000 customers on the wastewater side, a bit more on the water side, through our 32 wholesale customers.
All right. And then a quick intro for the company I work for, Burns and McDonnell. We're a 100% employee-owned engineering, architecture, construction firm. Our headquarters is in Kansas City, Missouri. We've got sales around $7.5 billion a year, and we cover about 12 major industries, of which water is one of those. Got about 12,000 employee owners in the firm across 75 offices. Water's been sort of a foundational part of the work that we do. It was one of the very first pieces of work we did as a company over 125 years ago. And because of our location in Kansas City, Missouri, we've been working with the city of Kansas City, Missouri for the better part of a century on their water and their wastewater project. So we've got a long history working together as a city and as a firm, and Blake and I have kind of a long history working together as an owner and a consultant. So I know that we have a lot of people on this webinar who probably are water, wastewater sort of people, but given the sort of really wide umbrella that AES has in terms of environmental engineering professionals, we were going to take a few minutes to just talk a little wastewater 101 to give people some context in when we talk about the needs of the project and the drivers of the project. So I was going to talk for a few minutes about that and then pass it back to Blake to get specific on the drivers for this project. And he did a really good job before explaining how KC Water is a one water utility, right? They provide the water, they collect the water, they treat the water, they manage it through the whole cycle. And that's sort of what has to happen in communities all over the country where there are sources of drinking water, whether it be rivers or lakes or streams or the ocean. And that water gets treated to a drinking water standard and then delivered across sometimes hundreds of miles of piping to cities and businesses and factories that then use the water for whatever they're going to use it for. And ultimately that water, after it's used, goes down the drain into a collection system that is also owned and managed by the utility, and then conveyed to a treatment plant, which receives that water plus any other amount of water that might have leaked into the system as it travels hundreds of miles, sometimes back to the wastewater treatment plant, and then discharging it back to the river, the stream, the lake, the ocean, and having to meet water quality permits, not only for the drinking water, but also water quality requirements so you can properly dispose of the treated water into these bodies so that those water bodies are still safe for recreational purposes. Somewhere downstream, it's probably going to be somebody's drinking water source. There's all sorts of things driving the protection of our water resources, and Blake's utility has to manage it at both ends of that universe. So to get into a little bit of nuts and bolts, to give some context a little further about wastewater treatment, it's generally broken up into two big pieces. One is treating the liquids, one is treating the solids, and then within treating the liquids, it's most commonly broken up into two more phases, what we call primary treatment and secondary treatment. With primary treatment, it's a lot of physical treatment using physical separation. So the water comes into the plant and some of the larger debris is removed by screens, sometimes is ground up by comminutors, grit and small rocks and sand and things like that get dropped out through gravity. And then the heavier solids can get dropped out through a primary clarifier. Again, it's mostly a physical process. On the secondary treatment end is primarily driven by biological process, where microbiology is used to remove the oxygen demand out of the water, to remove high levels of ammonia, of phosphorus, of other nitrogen compounds, things that if you discharge it into the environment can have a detrimental effect on the ecology of the receiving stream. We have a pretty large hypoxic zone in the Gulf of Mexico, right, where the Mississippi River drains out into the ocean, and that's because there's things in that water that get discharged from point and non-point sources. They then get discharged into the Mississippi that then hit the ocean, and there's a huge oxygen demand from those contaminants that cause a depletion of oxygen in that local area, and then cause a die-off in these really large areas of the ocean around where major streams discharge out there. So the secondary treatment includes not only the tanks to hold the biological reactor, but also air compressors to supply air for aerobic treatment. There's sometimes tankage for treatment that's maybe anaerobic or anoxic. There's lots of recycling and pumping going on. Another clarification step to remove some of the biology that is being used for treatment. And then the treated water gets disinfected by a variety of methods and discharged into the environment. That's the big picture on how we treat wastewater. And that gives you an idea of the kind of things that we're trying to do here with this project. So Blake, do you want to take some background and drivers for this?
Thank you, Jeff. So our Todd Creek watershed is located in the northwest corner of Kansas City. Yellow lines are basically city limits. In general, similar to most cities, the airport was built out in the middle of nowhere, and the city is approaching that. So the original treatment plant was built basically as the airport treatment plant. One of the other challenges of sewering this area is we basically put the airport at the top of 2 or 3 watersheds. So we basically have to sewer everything around it independently, which kind of increase our costs. And in general, this is a pretty, as you can tell from the map, it's slightly urbanized, particularly along that interstate corridor. You can see kind of east and south of that line. The rest of it's pretty undeveloped. So the original treatment plant was basically the steel basins you can kind of see on the left side. Those were built in the 1960s. In the 1990s, we did an upgrade for additional capacity by adding a clarifier to the right. Solids handling is done a little more similar to what smaller plants do, where the solids produced are basically sent over these holding cells. They cook for about 3 years, hence 3 cells. Fill one each year, then move on to the next, and then empty one each year. The material is basically stabilized. It's tested, shown that it's stabilized, and then basically land applied on nearby agricultural fields. UV disinfection facility was added in the 2000s, and the outfall you can see is into Todd Creek. As you can see, goes right through the plant. It's also a pretty small stream, so there's generally pretty heavy water quality, pretty restricted water quality standards, because basically the stream dries up in the summer. So whatever water quality standards Missouri Department of Natural Resources has for the stream are basically what our plant has to meet pretty much year round.
I think I'm going to keep it with you on the project drivers, right?
So as I mentioned, to the creek, we've had floodplain revisions. This is pretty common, particularly when there's upstream development in a watershed. The kind of red lines are floodway, which, if you've dealt with the Corps of Engineers, is the don't build there unless you absolutely positively have to. And the kind of cyan blue is floodplain, which is you can build there, but you basically have to dig a hole somewhere else to allow equivalent water flow. What this doesn't quite show is that where those floodplains end, particularly on the north side, is a fairly steep hill. For those of you not familiar with Missouri, pretty much most of Missouri, pretty rolling hills. So we pretty much have no buildable space that's not in the floodplain in this area. So the existing plant site is not a very good one, and that's without even thinking about having to raise an access road to the 100 or 500 year flood elevations to be able to safely access the facility, because it's great to build a facility that's protected, but if you can't get staff there, what are you gonna do about it? So next slide. So this shows a little bit more in depth of kind of the development that's going on. So the area the area kind of been branded Twin Creeks south of that. So the eastern half of that is kind of designated for residential growth. And the tricky part from us on the development side is the western portion is set for industrial development. So with us, that makes designing and sizing a plant pretty hard because you could get, say, an Amazon warehouse where you've got 50 people, very low pollutant loads. You could get a very large data center and get basically a river of saline water coming in you have to deal with, but no other pollutants, which kind of messes up the biology Jeff discussed, and we'll talk about a little further later. Or it could be, say, a food processing plant or sports drinks or something where you're dropping the equivalent of a 50,000 person city worth of waste on it. So it's very hard to plan for those loads. And so here's a little bit on just a little bit more in depth on the zoning. So the blue is residential, and kind of the cyan on the upper left is the area set for industrial development, and kind of all of that area is queued in to come into this treatment plant. And as Department of the City, I mean, it is very important that we provide the services necessary for growth in a timely manner to allow for those projects and jobs to come in, but also not overbuild it and waste our ratepayer money, or be paying bonds for 20 years and not receiving any revenue for the capacity we just built. So it's a delicate balancing act for us, and that's helped drive some of our decision making. And so just overall, the current flow rate going to the plant's about 2 MGD. Our plan build out for 20-year period about doubles it. And then just for an idea, our current that's projected to be about 25,000 people, and then about almost the same equivalent in industrial in this area. And so the question mentioned, so so most of this watershed's not built out. So we kind of basically figured out, so what's the maximum potential growth we can have? Because there's certain things that are very expensive after a plant is built to upgrade. So those you tend to build out or build half. So right now we're guessing, which considering how accurate everyone is with guessing what the populations of areas are going to be. You can talk to the Austin City planners 20 years ago and see if they guessed right. But our guess is 2021. Sorry, the end of the century will basically have this watershed fully built out at around 70 MGD. But we're trying to guess on that knee of the curve, that basically where the curve starts to go exponential, and kind of guessing how much we need, but also have enough land to be able to build for that full build out. And I think you're going to take over on the condition assessment, Jeff.
Sure. So a couple of the other drivers, one of them was that it's the condition of the facility. You know, as Blake told you a few slides back, basins 2 and 3 have been there since the 1960s, and they're steel tanks. Basin number 1's a concrete tank, so it's in better shape. But you know, various parts of this plant have been around and in service for 50 plus years. And in a wastewater plant, 50 years is way more than a lifetime. And so from both a structural standpoint, in a lot of cases, definitely from an electrical standpoint, a lot of the assets at this facility are way beyond their expected life. The operations and maintenance staff for KC Water has done a really fantastic job in keeping things alive for a really long time. But the risk of failure at this point is a big issue because you know, based on the development that's been going on in the Todd Creek sewer shed, the allowable downtime for any one of these basins is very short, because they do get a lot of flow relative to the size of the plant. And so you can't have you can't have basin number 1 down for very long without taking on a lot of risk. And so the risk equation started to really push the decision to do a plant expansion. If you know, if you look at a few of these pictures, The wastewater basins themselves, you see this one's full. The next picture is when the water's been brought down. Just a lot of corrosion in the steel tank. When you measure the wall thickness, it's starting to get pretty thin. It's a bolted steel tank. And then in addition, the electrical gear, although it has been replaced periodically, it's really at the end of its life for a large fraction of the electrical and mechanical systems. And so then you start getting into not only code compliance, but safety, and just you get sort of dogpiled in terms of the drivers from a facility condition standpoint to make this change. The other thing that comes up is, in particular, when you're going to build an expansion on a wastewater plant, there's a reconsideration of the water quality permit, right? There's a discharge permit that establishes what the water quality needs to be. A lot of drivers going on when it comes to a water quality permit. It can be as simple as, hey, you're doubling the size of the plant, so now your water quality needs to be twice as good, because there's a concept known as anti-degradation, which means you can't make the receiving stream worse due to your project. And since we talk about mass loading of contaminants into streams, if you put out twice as much water, you need to cut the concentration down by half. I'm sure all the AAES people can do that kind of math in their head and see how that makes sense. So we did go through a pretty extensive review of water quality and anti-degradation study. In addition to the adjustment of water quality parameters based on flow, the state of Missouri is also making water quality requirements more stringent across the board, in particular for nutrients. There's ammonia regulations for mussels. There's going to be phosphorus regulations put in place in 2035, which is within the operational lifetime of this project. So the ability to remove phosphorus has to be incorporated into the design. And then later on down the road at a date to be determined, there's total nitrogen requirements, that TN, listed over there on the right. And that requires a certain kind of process to remove total nitrogen versus just ammonia. And then lastly, during the original concept development of the project, Kansas City was undergoing a major renovation of its international airport, and the spent aviation de-icing fluid, SADF, was potentially going to be sent on to Todd Creek in the wintertime after they de-ice the planes. That would potentially introduce a huge BOD load to the plant that would have to be managed by a really flexible treatment system. Now, a few years later, that SADF is probably going to be managed differently through a recycling program. But the challenge remains because, as Blake suggested, some of that industrial commercial development that's being encouraged in the Todd Creek sewer shed could be a sports drink manufacturer. It could be a foods manufacturer. It could be something that puts down a really strong organic load into the sanitary sewer. So the presence or absence of this SADF became a little bit of a non-issue, because either way, the treatment system had to be designed to handle some pretty high organic loading so that they could support the development that the city wanted within that sewer shed. And so, we had to look at not only the commercial and residential, the seasonal glycol loadings / seasonal industrial loadings for the plants, and that helped to drive the selection of the process technology that was used at the wastewater plant that we'll get into here in just a minute. Okay, Blake, says you or me?
I can go through this. So in general, a good deal of the traditional funding for water and wastewater infrastructure comes from basically the federal government sends money to states as part of the kind of the delegated authority that was set up with EPA. They then administer a loan program. It's basically low interest loans. Typically, it's around it's a 3/4 reduction, basically the interest rates the Fed receives, which, hey, 10 years ago that was okay. Now that's amazing. It's a great program. So, but that process requires alternatives analysis. So we looked at four different technologies on this.
Okay. And then I can roll through the technologies here.
So one thing about how KC Water does its evaluations, we tend to look holistically. We do a modification of kind of the standard triple bottom line by adding an operations component. When we were starting to roll this out, we just found that trying to squeeze how our operators interact with our projects into social or environment, sort of, particularly when we try to squeeze into social. I mean, sometimes those views are what is most convenient for the operators to do, and what is best for the public are kind of at odds. So having them as a separate category just helps us with that. And then in general, on us, we found that equal weighting between all these just doesn't match our standard decision-making process. We generally go with, yeah.
Yeah. I was gonna say when we work with KC Water on these sort of topics, we have a number of criteria broken up between those 4 quadruple bottom line categories, right? And they can range in the environmental categories, the things that you would think about, right? What's the resource recovery potential? What's the greenhouse gas emissions potential? What's the protecting ground and surface water? When you're talking about the community, it's more of the community that they're serving as well as the community that's near the project. So, how does that enhance the public health and safety? But at the same time, what are the construction impacts? Under the financial category, it's the 2 big ones, right? It's the total capital and operating cost. But it's also a thing about risk, right? We can project that the project costs some X number of dollars, but based on the technology, based on the plan, what's the likelihood that that number ends up being something really different? Is the city taking on a risk that's very certain? Is it a low probability risk, or is it a high probability risk from an economic standpoint? And then to Blake's point about operations, there's a lot of criteria that matter to operators, right? What are the equipment requirements? What's the skills and competencies needed to run the technology? How safe can it be? What are the total manpower requirements? Because that goes to staffing and that goes to labor costs for the utility. So for each project, we work with the city to weight each one of these criteria and then evaluate the treatment technology options based on this weighting. And so you can see here for Todd Creek, there was a lot of weighting put on total capital and operating cost, which is really common because they do have to be good stewards of the ratepayer. But they also want to make sure the risk level is commensurate. They want to make sure that it's a safe facility. And so these criteria vary from project to project. We did an initial workshop to look at how the design team scored each one of these alternatives and check and see how the city feels about that scoring, and talk to operations, talk to engineering, see how the scoring might need to be changed to reflect the reality on the ground for them. And then came back in workshop 2 to present the final analysis and make our recommendation as to what technology is the right one for the project. So I'm going to talk about those 4 options at sort of a high level so everybody understands what they are and the kind of pros and cons that they would have brought to the project. The first one we call the MBR hybrid. MBR stands for membrane bioreactor, and it's a treatment technology that is a small footprint design option. It's really suitable for places where you either need a very high water quality or you have limited space to develop the project. So the thought was we could potentially stay within the footprint of the existing treatment plant within the city's existing property boundaries, do the expansion, do the improvement to water quality, and kind of simplify the overall effort using an advanced technology. Couple challenges with this though. Number one, it's a relatively expensive technology from a capital and operating cost standpoint, not dramatically so, but it does have an impact. And when capital and operating costs are highly weighted on the screening, it does translate into an impact. But more importantly, you can place the new facilities in the existing footprint, but it doesn't take away the challenge of the floodplain. In particular, if you're surrounded by land that can't be developed in the future. So your ability to expand is essentially curtailed. In addition, the access road to get to the plant is essentially planned to be underwater. And so you might have a great plant, but it's not helpful if you can't get to it. And so the cost to put up flood walls and other flood protection measures just to protect an access road added to the cost. And it also was from a permitting and standpoint really infeasible, because when you do all these things to provide access, you're taking certain amounts of land outside of the floodplain then, and you have to find replacement areas to be new floodplain. So you have to do that sort of offset to support stormwater management. And like Blake said, this is sort of in a valley next to a hill. There's no great options to mitigate the flood situation. So technologically, great solution. From a practicality standpoint, a lot of uphill. Option 2 is what's called A2O, which is just an acronym for the type of biological processes that would happen. It's anaerobic, and then anoxic, and then oxic, shown in this box chart over here. That's AAO, A2O. It's a really conventional and familiar treatment system. It does a really good job. It's relatively robust, pretty straightforward design, and lots of technology vendors can supply this equipment, which is good from a competitive bidding standpoint. It's also relatively expandable, but it does have a certain amount of footprint that's required. And the primary downside of it is it had a relatively high operating cost, because it takes a substantial amount of air, especially for this oxic process, especially for this internal recycle. If you see this 100% to 300% influent return, that's a lot of water. That's a lot of pumps that have to operate 24/7. And then lastly, looking at the probable water quality requirements in the future, there'd be a pretty significant amount of chemical needed to supplement the biology to meet the water quality requirements in the future. So looking at the overall life cycle cost, it was relatively high, various to some of the other options. If you'll notice, though, this plan and the remaining 2 alternatives are all looked at a different property. None of these, outside of option 1, can fit on the existing property. Okay. Option 3 is what's called an oxidation ditch. It's kind of similar to A2O conceptually, but from a practical construction standpoint, it looks like a sort of an oval racetrack with the water moving through this track, going back and forth, being driven by surface mixers downstream of some other larger basins. It still uses an anoxic basins and anaerobic basins and aerobic basins. It's just in a different configuration. And what the oxidation ditch brings to the table is it's very robust. It's very redundant. So when you think of potential high organic slug flows that might come in, it's really good at handling them, and it's reliable, and it is mechanically simple. The downside of oxidation ditch is it's got a pretty big footprint. And so even though we're looking at moving the plant to an alternative site in this option, there's a cost to property procurement. And so expansion, you have to think about overall what that's going to do to the amount of acreage needed at the site. And from a construction cost standpoint, these relatively big basins take a lot of concrete. And especially now, concrete's relatively expensive. And so it does impact both the procurement cost and the construction cost for the project. Lastly, we looked at what's called AGS, aerobic granular sludge. And it's a little bit different technology. It has been around for a few decades, but it's younger than the other technologies that we were showing before. What this does is the same aerobic, anaerobic, anoxic sorts of treatments, but the biology that exists in the water, instead of being kind of a fluffy mass of biology, the process is operated to generate more of like a granular biomass. And you can see in this cartoon, it's symbolized with these granules that are, they're a couple millimeters in diameters, maybe. So these aren't big, they're still very small, but they're many times heavier than the biology that would exist in the other treatment basins. And so what happens is you get the kind of treatment that you want, but when you want to settle out the biology and extract the clean water, it can happen much, much faster. And it can happen in a smaller basin because these little granules will sink very fast. Whereas in the other technologies, that biology sinks relatively slowly, and you need more time and more basin to make that work. In addition, this granular sludge has a slightly lower oxygen demand, and they do tend to perform better in terms of removing those nutrients, those nitrogen compounds and phosphorus. And so it's really a technology tuned towards nutrient removal, which is a key facet of this project. The downside of AGS is kind of twofold. One is it's a relatively new technology. So from a permitting standpoint, and we'll talk about this, the state of Missouri had some trepidation that we had to work through. And number two, you're primarily paying for the technology. The cost for the basins isn't that much because the basins are relatively small, but there's an intellectual property piece here that you have to pay for, and it is not small. So looking at those four technologies, we went through that weighting system. There's two different workshops that Blake talked about, weighting the different alternatives, pros and cons. Generally, big numbers are better. Small and negative numbers are worse. And you can see, kind of based on the things I talked about and the scoring, that the AGS system comes out overall with a better score. Some of the big drivers, the MBR was really pretty expensive, in part because of the technology, but also in part because of the flood mitigation that even that couldn't work in real life anyway. And some of the other drivers were environmental considerations, although they all have a really positive effect on the environment. And some of the operational considerations where you talk about operational complexity and simplicity. So our recommendation to KC Water was to move forward with the design of an AGS-based facility. All right, just so we're going to move forward and show some of the concept design and just sort of summarize the benefits that this technology is going to bring to the project. It was the lowest overall capital cost for the project, and it also had the lowest operating cost for the project, primarily because there's no internal recycle. So you're not pumping 300% of the flow internally over and over again. The operation is relatively simple. You don't have clarifiers, which, although clarifiers are a simple concept, operating a clarifier right takes a pretty skilled operator. It's almost an art as much as it is a science. And so OpEx was improved by AGS. It has a really good water quality performance, meeting the anticipated water quality requirements now and in the future. A big thing that Blake mentioned before is in terms of phasing. This system can be designed in a really modular fashion. Some of the other technologies weren't as amenable to a modular approach. And as this watershed gets built out over the next 60 years or so, 70 years, we do want to be able to build what's necessary, but not overbuild, so that KC Water can continue to be good stewards of the ratepayers' money. And so being able to phase is really important. And finally, from an aesthetic standpoint, it's got the smallest footprint that goes to the cost of property acquisition. It also goes towards being a good neighbor, so that folks who are building in that watershed don't have a massive wastewater plant they have to contend with for various reasons. I talked about permitting just briefly, but what's happened is, the Missouri Department of Natural Resources, which issues the operating permit and approves the overall plan, does have in their state regulations requirements for how they address new technologies. And they have three ways of doing it that you have an option to consider. One is they will approve what they consider to be a new technology through direct approval. What you have to do is provide good operating history. They want 3 sites operating for at least 12 months in what they consider to be a similar size, influent composition, and climate. At the time that this project was being developed, that did not exist. Now, this AGS technology has been around for maybe 15 years, maybe more, but a lot of the sites were either, were primarily overseas. The few sites that were within the US didn't have a long operating history, or they weren't in the same type of climate zone. So those weren't acceptable. And kind of to our surprise, it was really difficult to find a site from Europe that not only met the the climate and influent composition, but where that data was able to be shared by the utility. Information sharing and transparency in Europe is really pretty different from it is in the United States. And so we weren't able to get direct approval. You could do a pilot project running for a year, sending the treated water back to the existing wastewater plant with an approved and testing plan. But due to the potential drivers on this project at the time, there were a lot of interest from industry in building something right away that they would need this plant for. The city chose to move forward with a demonstration project, which meant you build the plant, you get it running, and then you run it for 1 year with a more enhanced testing program and a reporting program, just to show in a pretty exhaustive manner, hey, this thing is running as it should, it's treating as it should be treating, and the water quality is meeting everything that we'd expect it to. So the plan at the time was to move forward with a demonstration program. All right, very quickly, I'm just going to go through what the current design looks like generally, give you a few artist renderings, and then I think we'll have time to take any questions that the folks in the webinar might have. There's a number of buildings on the site. The site's on a pretty big slope, so there's a good amount of cut and fill and hilling and embankment, as you can see in the civil plan. We have a AGS structure, which you'll see in the artist rendering is really a series of basins tied together into one long concrete structure, along with piping and pumping. Next to that, we have a blower building, which surprisingly holds blowers. Immediately north of that, we handle the solids that come off of the biological process in the solids building, where we stabilize the solids, allow it to be properly disposed of. There's an administration building as part of the project, which allows for operations training, a pretty nice laboratory, and basically a good meeting space so that the folks who are operating these plants in the north side of Kansas City have a place where they can all group together and do the things they need to do for meetings and planning and discussion. It's something that really doesn't exist right now for these north plants. Finally, the treated water will go through a UV disinfection system that'll then discharge that disinfected water into Todd Creek. Okay, a few artist renderings. You can see the artist rendering here in the lower right. It's a long concrete series of basins tied together. But what this doesn't show is sort of beneath the skin of this, there's a lot of long runs of piping, automated valves, a pumping gallery to manage solids and adjust water flows, and access ramps and staircases to get up and around the basin. So there's a lot of parts and pieces that go on inside and outside of the AGS basin itself. The solids handling building, I'm showing it here with a little bit of the roof stripped off. There's 2 basins that are used to hold and allow the sludge to be thickened and stabilized, so it can be taken out off-site for proper disposal. And then inside the building itself, there's equipment for thickening and pumping and adding polymer to the sludge as needed to do the right kind of processing. The disinfection building, the process itself is in below ground trenches where a series of UV bulbs are used to deactivate pathogens. And then we've also provided with the disinfection facility 2 other elements of the job, a non-potable water system, which is this blue prefab shelter right here to provide non-potable water across the plant. And then inside the building, there's actually a maintenance area for the O&M staff to be able to do maintenance indoors, do some welding indoors under safe conditions, have storage, and just have a work area where they really don't have that opportunity in other plants in the north part of town. And then I mentioned the admin and lab facility. They're all sort of following a similar blue and tan sort of color scheme. And so this facility not only has offices for operations staff, meeting rooms, a pretty exhaustive lab, and a good place for those operators, both from Todd Creek and the other 2 Northland plants, to come and work together as needed. So last couple bits. The original budget of the project was in the $60 to $80 million range. As of right now, it's looking to be around $108 million. And you might say, well, why is that? And I think we all know that inflation has not been awesome to construction projects, whether it be the cost of materials, the impact of skilled labor availability, things like that. There's been a pretty dramatic change in construction costs for all capital projects, for all cities and all utilities. It's something that Blake and his folks are having to really scramble to deal with all the time. So, and then lastly, the project schedule. We started this project sort of around COVID times, went through facility plan and design and wrapped it up in April 2023. There was a pause to deal with some property procurement and evaluation to get the final design right. And then as soon as we get past that piece, which is kind of happening right now, we're projecting a little bit of revised design based on what the property procurement looks like. And then that should allow the bid to happen in the summer of next year. And it's about a 30 or so month construction plan to have it up and running in January 2028. One thing I'd point out is where it says site restoration, something I kind of neglected to say before. Since we're moving the plant, putting on a new property, the city is going to demo the existing wastewater plant and let that site be, go back to nature, be part of the floodplain, and just sort of restore that site back to natural conditions. I think that's the end of our presentation. We've got anything else, Blake?
Nope, I think you covered it pretty well, Jeff.
All right. So happy to take any questions that you got, Dan.
Fantastic, Jeff, Blake. Thank you so much. Fantastic presentation. So now what I'll suggest, maybe we'll pull down the slides so that people will be able to see our smiling faces. So maybe if you stop it there, and then we'll go from there. I really appreciate that. No, that was a fantastic presentation. So we've got a number of questions that have come in the chat and in the Q&A function. I've kind of put those together. So let me take it through kind of like, a series of questions, and then we'll come back and kind of pick them off a little bit at a time. So one may be a little bit more towards Blake at the beginning, but, KC Water background, right? So, we often think about drinking water utility and a wastewater utility. We've got a whole water. So did it start that way? Did it become that way? What's a little bit of that story? Kansas City's known as a city of fountains, right? So explain a little bit of that narrative of the city of fountains in there. And then we saw the diagram where it looked at the water system and the wastewater system. There was some combined flow on the wastewater side. So do you have combined sewers? Do you operate separate sanitary and storm? And then does the storm also hit the secondary treatment facilities? So there were some questions kind of in that space. Then there were some questions on the drivers of the design space. So that FEMA floodplain. So you talked about, if you borrow from the floodplain, you're going to have to give back to it somewhere. But that begets the question, all right, but are we really assuming that the weather is the same for the next 100 years? So how does a longer term weather view fit into how you're dealing with those handoffs in that floodplain? And then you talked about the idea of the spent aviation de-icing fluid, which raises the question of NPDES permits or pre-treatment, industrial treatment before they discharge to you. So how does that factor into your system? And then in particular, how were stakeholders engaged in planning for future land use, right? And how were government, how was industry involved? How were developers involved in those kind of conversations? Because you guys did a great job of highlighting there's a lot of options there in that space, but do you use some zoning to kind of limit those? Do you use some industrial pre-treatment to get, so maybe we'll talk a little bit about that. You talked about one of your criteria was risk. So Jeff, you highlighted that there's the cost, but then there's the risk with that. So do you manage that risk exclusively with the technology, which kind of seemed the way you were talking about it, or do you also manage it with financial instruments like insurance and bonds, right? So how do you manage risk? And is it just a technological risk management, or are there other ways of managing risk? This kind of gets into the space of resilience, CBAC question of climate, FEMA floodplains, et cetera. So how do we manage risk in a broad spectrum? Some of your design options. You talked about this new site, alternative site, right? And the flood control was highlighted as one of the costs for the MBR. was the MBR examined at the alternative site? Maybe we got a little confused in there, right? Because it seemed like that protecting the access road was something that was highlighted with the MBR, but not with the other three. Do they not need the access road, or are they going to be in a different? So maybe if you can, we'll get into that and tease apart the little of the details there. You talked about aerobic granular sludge. We didn't use the proprietary name of aqua narita or anything like that, but it looked like the diagram looked very similar to that one. So, maybe if you can speak, if there's some alternatives in that space, a little bit, is it just one granular sludge, or are there some, are there options within options? And then, because this kind of gets into this whole idea of running a pilot for a year to make Missouri DNR satisfied. So as we get into options within options and different versions of proprietary technology, do we end up having to repilot over and over again? I mean, it's all just some bacteria hooked together, right? So how much pilot data is needed to convince somebody that this thing will work? So, and then at the end, of course, we'll leave with the standard question of a consultant and a utility working together. What would be some advice that you would give to students who are looking at these careers, or to emerging professionals? How do you develop these kinds of relationships and nurture these kind of relationships? Obviously, a utility and a firm presenting together seamlessly, going back and forth, shows that great relationship. So we'd love to get some guidance so that folks can understand, how do they develop those skills to have those relationships, be they out of school into utilities or out of school into firms. How do they work back and forth across that? So that's kind of the discussion space we'll get into. I'll go back and kind of unpack those, but that hits a bunch of the questions, and there may be some more that come in, but that kind of hits where we were at. So if we go all the way back up, and this idea of Kansas City water in the background, the city of fountains, and we think about water utilities and wastewater utilities, Blake, what's the story there from?
So yeah, the city of fountains is not necessarily water related. It's more that when Kansas City was building out in the early 20th century, there was a concept of, instead of a park being a part of a city, having the entire city be a park. So the fountains are kind of core design. I'm an engineer, so when things that are beautiful, like, other people handle that, so I'm trying to explain that.
Oh,
But
yeah.
it's more that the fountains are kind of anchor points of beauty throughout the city, particularly our boulevard system. So that's kind of the idea behind the city of fountains. Water utility basically has been around since the 19th century. It was originally some private water utilities, and then as the city's expanded over time, that water utility has grown with the city. Wastewater. So embarrassingly enough, the started as the water pollution department in the 1950s. So we actually did not have even primary treatment for our main sewers when my father was born. So that is how behind and damaging. So we also conveniently had our water treatment plant upstream of our city. So were those two correlated? Yes. So eventually in the 90s, they decided to consolidate the two departments together just because of efficiencies and scales. For example, my group does all the work in the plants and pump stations on the water and wastewater side. For example, I'm an electrical engineer. Does it matter if it's powering a blower or if it matters if it's powering a pump? Not that much. Fairly similar skill sets, so that we can be efficient as the city as a whole, and also work together well. And so
Makes sense. That makes sense. Now that kind of helps explain how they came together. And so they're both it's essentially one utility owned by the city is basically how.
Legally 3 utilities and 1 department the city runs. So Missouri law is your rates have to pay for the service. So we have a wastewater, a stormwater, and a clean and a drinking water utility. There's been discussions about possibly setting up a reuse utility if we can get enough demand on that side as well.
Okay, fantastic. So that helps with some of the background. One of the things is the question about the combined sewers, the storm sewers, the sanitary. Do they all flow to the treatment works? Do they do some bypass, some storm bypass?
So
those are complicated questions, and if you've got the answers to those, we'd love to hear them.
So our urban core, which is probably about a third of our probably third to half of our population, is in a combined sewer area. It's basically before the mid 60s. Outside of that is separated. So the entire growth area we're talking about was in the separated sewer, and then kind of the southern end of our system is set up that way. So the combined sewer, or the stormwater that makes stormwater basically that gets conveyed, that gets put into the sewer, is then basically conveyed and treated at our wastewater treatment plants, or it overflows, depending on how extreme it is. Our general level of service is a 2-year. We're trying to approach, and everywhere is 5-year level of service and separated. So the 5-year storm, according to all those FEMA and actuarial tables, will basically be handled, and the 2-year storm in the combined sewer.
Makes sense. That makes sense. Now, thank you for that background on Kansas City Water and kind of what's going on with the collection system and the sewer system. So then looking at that, right, obviously this FEMA and the, what was the floodplain factored big into this kind of project, right? So, but how does that factor in? I mean, that's the floodplain from looking at the storms for the past 100 years, and now we're thinking about a design for the next 100 years. So whether we call it changing weather or climate change or whatever we want to call it, how does that factor in?
That goes more into the squishy part of our QBL when we do our quadruple bottom line analysis of just overall risks of, do we really want to put this much money in the floodplain? Because as people mentioned, like, floodplains don't stay constant. I mean, there are places that have had several 100-year storms in the last decade. Thankfully, we are not one of them, but these things happen. So just the risk of being near body water that can flood is bad. So that's the key. Our quadruple bottom line methodology sort of lets us, where our intuition is like this, there's some risk here, we can kind of push it to the other direction.
Okay, makes sense. Makes sense. And how were then the stakeholders engaged in looking at those land use issues? Because I mean, you talked about everything from, food to, a server farm to an Amazon warehouse, right? And the different kinds of loads and.
So anyone's worked for a city, you basically end up signing NDAs talking about development. So it has to be as vague and ambiguous as possible about an area. And so for good and ill, the sites we were looking at for this were actually owned by a developer who wanted very much for us to build a plant to add capacity for them. So the very act of trying to negotiate that purchase with the developer who's building an industrial park made that communication pretty clear. The tricky part where we got a little, we got snake bit pretty bad was land purchases. You usually keep them confidential until they get to a certain point. That took us past when we normally like doing our community outreach to the general public. Okay. So usually we like to do our community outreach starting at 30% design. So our preliminary design, we have kind of concepts, layouts, we can talk through some specifics with people, but it's early enough we can adjust. On this one, we did it much later, and there was definitely some community blowback on our side that we had to address. And so that's part of the reason for the project timeline is we actually end up changing sites.
Makes sense. Makes sense. So Jeff, maybe a couple questions kind of your direction as well. So, in terms of, getting this stakeholder analysis and then trying to give them a design and looking through it. So industrial pretreatment or NPDES for other point sources there, from industries in it, why have the city grab all the sewage and deal with it when you could kind of piece it out and give regulations to, to each discharger? If in this area, was it just too small to deal with that? Or is there not a history of that in this area? Or was that something that factored in at all, or the thought process?
Well, right. I mean, the one thing that probably the important thing that drove all this was that the city made sort of a very strategic plan to develop this watershed, this sewer shed, in kind of a thoughtful way. And drive commercial industrial development and drive residential development. And so in order to do that and attract those businesses, you have to be able to provide the utilities too. And so it's a decision on that end. And then you also have to balance that with all right, we got people coming. We don't really know who or when, but let's make sure we choose the technology and a configuration that can adapt to those things as they come to light.
It's a lot to factor in as the engineer doing a planning design, right?
Sure.
Make it really inexpensive. It'll do anything you want it to do, and we can build it like that. Perfect.
Do that every time.
the unicorn of design.
Right.
Of design. Well, so that kind of comes into one of your criteria. So you talked about risk, right? So it felt like you had an awful lot of kind of technology as part of the way to deal with risk. But was there any exploration around some of the finance as part of that? And that maybe comes back to the issue where you're like the city had kind of gotten their mind around here's what, here's what they're going to do. But are there financial instruments to help manage some of that risk as well? Either whether it's, bonding or insurance, it makes a left turn and the city's left holding the bag because they built this thing out, but then they don't end up with the right person moving in to use it. I mean, are there things that our members should be thinking about, Jeff, in terms of managing those kinds of risks with things in addition to technology?
I mean, I'll let Blake kind of elaborate on this, but basically, the city can either cash flow the work, or they can do a SRF loan, like a loan program, or a mix of those two things. But at the end of the day, because they're a city-owned utility, they're expected to be stewards of the ratepayers, and they have to be able to provide the ratepayers with an expectation of what the rates are going to be over some term. And so they are constantly trying to balance a list of necessary capital projects and a certain amount of money that they know is going to be coming in. And those two numbers, not surprisingly, never quite add up the way that they wish they would. And so they have to make those decisions on, well, gosh, is this project important enough and timely enough that we have to do something better than cash flowing it, and maybe take on some financial debt to make this thing happen. And Blake, I'll let you elaborate from there.
Yeah, I'd say lately we've been doing a little more bond sales on things, but I mean, in general, I think the comment is like the build it and they will come. So we do have a baseline flow to this plan. So I mean, we do have ratepayers and flows and requirements there. The question is, how much more do we build? And so in general, we've handled that risk more through site planning and layout, so that we can more quickly. So, for example, the AGS basins do not have secondary clarifiers. They have fewer unit processes. So the ability to spool up and build additional structures on site if someone comes into play. Because the thing about development is, well, it takes us time to build stuff, it also takes the developer time. So, I mean, in generally, the way we handle kind of that risk if they fall through is usually when it gets to a certain point of us actually building something, we require a commitment for, say, 10 or 20 years, the amount of time it'll take basically for those rates to pay back the infrastructure. So that's kind of how that's generally how we manage those risks. We usually have to go a little bit out on a leg, but that's how we manage it. In general, I'm not aware of any insurance instruments or bonds that would kind of cover growth risks like that, just because.
Okay. It just helps for the member here and see if there's things that are out there. So now then maybe yeah, you never know, right? It might be a market that's got some need, particularly as things get more and more expensive and weather gets less and less predictable. We might need to think about those things. I mean, we were talking Florida, they might be thinking that stuff a lot more already. So one of the things that we were talking about, Jeff, you had a lot of great details of the four alternatives and how to look at it. So people had some questions about the site, and maybe if you can help kind of get back in there. It felt like that the MBR was kind of constrained by existing sites, but then the other technologies could maybe be done on this other site. And then it felt like some of the language was like, well, and we also had to deal with, site access. And so therefore, if the MBR is on this, so can you help unpack that a little bit? Were there actually kind of multiple sites you were looking at, and were all the technologies examined basically at both of the sites, as it were, or can you explain that a little bit more to us? So
yeah, so absent any kind of site issue, a lot of times the reason you might choose MBR technologies if you had a really high water quality requirement. And the water quality that technology can put out is greater, significantly greater than the water quality that this project was going to require. So the real driver for choosing MBR was, could we develop an alternative that didn't require a new property, a new site? And once you got that there, you're like, okay, well, what else do we have to do to protect the site and provide access to the site and all those other things I mentioned about? If you were to take that option and move it to a new property, which I know that some of the questions were about that, the feasibility goes up, but you're sort of have a bit of overkill. All of a sudden, you're using a technology for the wrong reasons on that site. And while it would meet everything, it was still going to end up being expensive from a CapEx and an operational standpoint. And you'd have a water quality technology that's not really in line with what the project requires.
Get more into the thinking about if you had some water reuse, but we're in a fairly wet part of the world, so
that's right. You're not
plenty around. So
that's right. Yeah.
So that helps, right? And so then if you're, but were you considering an additional site, or is the current design to go with AGS on the existing site? Is that kind of where you're at right now?
The other alternatives outside of MBR, none of those could go on the existing site. And as you heard, we determined you couldn't even put MBR on the existing site because just getting site access, protecting the access roads, all that stuff, that floodplain pretty much kills the deal for whatever technology you're talking about. Unless we joked about maybe, buying hovercrafts or helicopters. That wasn't awesome for the project capital or operating costs, although the operators loved it. But that probably couldn't get included. So yeah, we are going to be on a different site, one that's at a much different elevation. But it also is really close to the existing site, so that in terms of, the buried sewer interceptor that comes to Todd Creek, we are just maybe 1,000 feet upstream on that pipe, right next to it. And so
Oh,
we're still very close to the existing infrastructure. We're just a little bit upstream of it, and it just happens to be nicely uphill.
perfect. It all just, everything aligned, right?
All just worked
Okay,
out.
well, because those were some of the questions. Folks were like, well, how are you going to move the influent to the new site? So let me see if I can parrot this back and get this right. So
Yeah.
so you started with, can we stay on the original site? And your answer was, for one of our 4 technologies, there was a possibility to stay on the same site. But then we have to ask ourselves, in a flood, can they get access to be able to maintain and operate that? And the answer was, well, then that just makes the cost go overboard. So now we can take all 4 alternatives and go to a new site. And then we get this membrane system that's producing effluent quality that's way more than we need. And it's not that we don't want to have good quality. It's just we don't want to pay for something we don't need. And so these others work very well. And hence then AGS kind of falls out. Is that a
Right.
fair way to describe? Okay.
That's exactly right.
Okay, that makes sense. That makes sense. And so then when you think about AGS, right? And so then so for full disclosure, so I actually Mark Van Loosdrecht was one of my examiners for getting my own PhD. So I've heard lots about this technology over the years, right? So there's different flavors and varieties out there, but when you're thinking about granular sludge and you're thinking about AGS, right? So for folks that are looking at that as kind of a design option, is that essentially the way you would characterize it? It's like the A2O or a Bardentfo it's in that space of the nutrients, but you've got a sludge that's tighter and settles better. And so can you help explain to people, so that you did a great 101, but can you help explain to people kind of how that one's working differently than
Yeah.
the fluff of the flock?
From a microbiology standpoint, they're all sort of behaving the same because they're using the microbiology in different types of oxic environments to do the thing they do best in an anaerobic condition and an aerobic condition. The real difference here is that you're providing an environment that helps to generate this granular form of sludge, whereas normal sludge is a lot more flocculent, it's a little more fluffy, and it floats around. And what that gives you is an opportunity to have faster settling of the sludge, which is a key operation in wastewater where you need to separate the solids from the treated liquids. And there's a fair amount of cost involved in settling out solids, and skill and operations complexity. So you sort of jump around all those things and come up with a smaller footprint. The microbiology isn't different at all. And in fact, even the way that the aerobic granular sludge reactors are designed is very similar to a common technology called a sequencing batch reactor. So those of us in wastewater, if you have a chemical engineering degree, you know what a batch reactor is and a sequencing batch reactor. It's familiar technology. The only real difference here is what we're trying to get the biology to do physically, but what they're doing biologically is exactly the same.
Got it. Okay, so we've got a physical process that's different, biological process kind of the same there. And so then convincing regulators that this new thing is the same as the stuff they know and trust, but yet it's new. And so you've got to do this kind of 1 year and a pilot. And you talked about this intellectual property and the kind of these fees. And so then I pay the fees for one kind of intellectual property, but then I end up with, subversion 4 versus, so can you explain a little bit how that process works? I think both from the both from the utility side about, okay, when I go to my regulator, how do I convince them? And also from the consultant side, how do I convince my utility that it's worth the effort to educate the regulator that this is same biology, maybe different physics, but don't worry, trust us, it'll work. Can you speak
Right.
to that a little bit?
Well, you know, I think you have to go back and think about what the regulator's obligations are, right? And fundamentally, if there's a environmental issue, if there's a water quality issue, a pollution issue, that comes back on them pretty quickly. It also comes back on the utility. They own the permit, but the onus on the regulators is to be comfortable enough with the technical solution that they will issue an operating permit to the utility. And so they have to be comfortable from a technical standpoint. And, you know, they've got a couple of ways to do it. And it really breaks off into two categories. Do we know enough about it? Is there a history we can look at that says, oh, this site, A, B, and C, is just like your site? Okay, that's fine. Or if you don't have that, it's okay, you can go with it based on some limited information, but we want to see how this thing operates. You can do it at a pilot scale, you can do it at full scale, but we're going to make you report more information early on so that we can reinforce our confidence that this thing is going to work. You know, and if conceivably, if the information came back bad, you'd have to make modifications in your project to make sure that you're providing the level of performance that the state wants to see.
Okay. Is that, and Blake, so how do you guys manage that? Because you've got the consultants over here, right? Some skin in the game, but you know, it's like they've got this great idea and you're like, well, but I got my regulator and this isn't my only permit. And this isn't, because as you've got multiple facilities out. Yeah.
Well, this is where the fact that we are right next to a state line matters, because there's basically a AGS plant that's within 50% of the capacity of this plant in our metro, just on the other side of the state line.
Okay. Okay.
I'm like, oh, it worked for them. Okay. So in that case, I'm just as a utility, I'm like, okay, we need the cost savings. We'll run the risk. Put it out there, it should be fine.
So from your standpoint, maybe the regulator needed convincing, but as a utility, the state boundary didn't stop you from trusting the data. Maybe for the regulator, they wanted a little bit on.
Well, it's also, if we go back to, we have a small rate base and a low population density. Like, I cannot have projects that are 100% risk-free on the process side and actually not kill my ratepayers. So there, we have to selectively take risks on projects, and then and make sure there's an issue, we can go back and fix it at lower cost, like adding a clarifier to a job or something like that, something where it's not a huge burden to add that price. But if we don't, then we can save that and roll it into another project.
You know, maybe the other piece to consider is that the folks at MDNR, they don't get to decide how they approve or don't approve something. What they've got is a really prescriptive approach that they have to follow. And so they may look at it and in their personal opinion, maybe this is totally fine, but they have to read what the state code says and follow the state code. So they've got their own limitations too, that the utility gets to make you know, risk decisions in a different way.
Makes sense. Makes sense. Well, along those lines, we had a specific question that kind of came in while we were talking that was looking at UV disinfection. So is there a requirement on your existing NPDES for disinfection? And if so, how do you do it now? And then would you look at UV as something, and how does that fit into? So I don't know, maybe you don't have a disinfection requirement currently.
We have seasonal disinfection, systems UV. It's been that way for 10 years. I think about 10 years for us, somewhere ballpark around that. So.
Yeah.
And
the
Jeff,
new facility will have UV disinfection also.
And from the trade-off standpoint, oxidation ditch A2O, you know, fluffy flock, right? Versus MBR, essentially nothing coming out, and granules essentially, you know, a pea size, you know, small thing coming out. So, you know, UV would work on some, but not on others, or how would that play into it?
No, you know, given the nature of the wastewater, UV would have worked with any of those really well. I mean, it's the predominant form of disinfection in the Midwest, and especially true with KC water. The other thing I have to think about with granular sludge is that, you know, everything's in a distribution, right? You have all these granules of a certain size, but there's some granules that are smaller, and you do still have a flocculent fraction in the sludge. And so, you know, it is true that you can have a slightly higher TSS, a total suspended solids, coming out of that effluent from an AGS reactor than you would out of a conventional secondary settling situation, because you're settling faster and you're letting the water out faster. So we did have to talk to the technology provider a little bit and talk to the UV technology provider a little bit to make sure that that was still a reasonable application of the technology. It is. And when you look at operating installations that utilize UV disinfection, it works just fine.
Sure. We had a question, maybe one final technical one before we pivot over to kind of how students or emerging professionals would prepare themselves. But there's a question around the microbiology of how the granules form, right? So Jeff, I don't know if one of you want to just touch a little bit on how that shear works and go from, because if folks get settling with conventional, then it's kind of the next step to granule. But maybe if you want to explain that.
It's an interesting science. It's still kind of being developed, but overall, it's a matter of not only providing a little more time for the biology, but also providing a little calmer and not as vigorous of a mixing situation so that those granules can develop. And it's actually a biological skeletal framework that the microbiology generates. And its true reasons for existing outside of wastewater are still sort of a matter of some debate. But some of it is a matter of evolutionary survival for some of these species. But you have to provide the right environment for the granules to develop like that. A little calmer reactor, a little longer holding times. There's some technologies that use hydrocyclones to physically separate the lighter and the heavier fractions so that you put a bias in the system towards the heavier, denser granules. That's not the case with this technology. They let it develop naturally. So that does mean that the biology development period will be slightly longer during startup than it would be otherwise. On the plus side, while you're waiting for those granules to develop, the system operates like a conventional sequencing batch reactor. So you can still get the water quality you want. You don't get the same performance. So the granules are relatively robust. And one of the reasons that we chose them in that they're very good at handling slug loads. They're very good at handling, deficiencies or excesses in oxygen that might happen from a operational incident from time to time. So because of their nature, because they're really created by the biology to protect the biology in nature, it helps with some of the variability you might get in a wastewater plant.
Perfect. Thanks, Jeff. Appreciate it. There had been a question about, is there some table where you compare the four and look at lifespan and cost? And so maybe we'll put that, because we'll take the PowerPoint and put them up as a PDF. And so maybe there might be some design report things that you can share with us there so we can make sure we get it back. I didn't want folks to think we were avoiding that, but they may, didn't recall exactly that figure in your presentation. So maybe we can get that figure if you contact us.
It's sort of buried in the QBL economic component for total cost of ownership.
That's right.
So I saw signs of it being there, but I didn't see it which is fine.
Yeah.
But maybe we can get that and add it in the PDF of the PowerPoint at the end. So students, second career, moving over professionals, emerging professionals, right? I try not to use the student and young professional because young seems like age, and there's a whole lot of reasons for people to be in different spaces where they're asking themselves, hey, is this the space for me to work in, right? So utility, consultant, partnerships, delivering this fantastic presentation, working on these things together. What are some of the skill sets that people need to be able to be successful here, whether they're on the utility owner side or whether they're on the delivery consultant design side? What are some of the skill sets that people should be looking to develop so they can be effective in these kinds of fantastic award-winning partnerships?
Blake, you want to take the first swing at that?
My general answer is usually empathy. You need to understand the other person, what their motivations, what their drivers are, what they really are, even if you don't ever tell them what they are. And then once you understand what motivates people and what they need, then that helps you to figure out how to mesh well with them.
Excellent.
Yeah, that's funny. I was going to say kind of something similar because you take exception to all the technical training that we get as engineers and scientists and everything, and at the end of the day, the best way, talking about it from a consultant standpoint, the best way to do our job is to make sure we have a really good understanding of what Blake's job is. He's not hiring me for fun. He's hiring me because he needs something. And if I can better understand not only what he needs from a technical standpoint, but all the things that surround it. Like, when does he need stuff? Why does he need stuff? Who's going to be harassing him about things? And what's the end that they really want? And that all goes back to communication and spending time with people and just kind of understanding the bigger picture on stuff, outside of how many gallons and how many square yards and how many what's the wire size. You gotta spend time investing into what people's situations are so that you give them the full and better answer.
Fantastic. Blake, Jeff, fantastic presentation. Congratulations again on your E3S award. We really, we were so excited that we were able to take time out to do this webinar for us. So we will turn it over to Marissa to close this out for us. But Blake and Jeff, thank you so much.
Thank you.
Okay, thanks everyone for all your questions, and thank you to Jeff and Blake for sharing your knowledge with us today. We have several webinars planned in the near future, so you can go to aaees.org/events to reserve your spot. And board certified members will get their PDH certificates for this event sometime this week. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day.